2 minutes.
Two.
Weasels.
Weasels.
Pop kills weasel.
Involve right an equation of weasel population. So 8t is equal to e to the 3. No. That's not right. Yeah. Something like 2. Because it double. Is it 3? Sorry, it's 3. I do know it's 37 years. I know that we're changing still British.
I remember it's 12 to the 3T.
I don't know. Because there's 12, 3k to the there's 12 weasels on every right?
Yeah, so it's 12E to the 3KT.
I thought it was 12 plus.
No.
This is the
Do you have to find K using
No, because it's A not equal, or A not equal K.
Oh yeah. 12 E.
that makes sense because then you have 12.
What's K then though?
K is the that, yeah.
So it doubles every 3 years. So that means it's like I know you use natural law somehow in this.
No.
I thought I remember seeing that.
No,
I thought they had like
when you solve it, you use that.
Oh, okay.
So then for V, write an equation for weasel population times P using exponential basis. Oh, so then you just
I haven't got it yet.
Using exponential
oh, I think was that exponential the other way?
All I can remember is
Yeah, I know. I don't even remember that.
I don't know what he's talking about.
Gosh, we did so many of these problems in Canada.
Yeah, no, I can't find it in my notes.
Oh, if time 3, oh no, that's not what I meant to do. Forget I said that. If time 3 is put in, that goes away. It's either the natural log of 2, which is 2, 12 times 2 doubles, boom, we're good. Okay? Now, this one. Carla, you got it. What'd you say?
12 times 2 to the 2 over 3.
Yeah. E's a great thing, especially as a calculus person, because its derivative is so cool, right? But in terms of logic, wouldn't it be more logical to take 12 and multiply it by 2 so many times? You're done. So it's a more logical base. And the 3 component to it is to shorten the period or stretch the period. All right? Are we cool? All right, now, how can I show that these are equivalent or coincide? You could sub one into each other. Play with this one, will you? In order to use a skill that we might need later on in this lesson, using exponent rules, how can you play with those exponents a little? This is all multiplying, right? And multiplication is commutative, yes? And so the order in which you do things doesn't matter. So I'm going to say, I'm going to take e to the natural log of 2 first, then to the third, and to the t, yeah? Or to the t over 3, excuse me, yes, t over 3. I mean to say. Yeah? Well, what's e to the natural log of 2? 2. And so, boom, yeah. Oops, there's no e there. 12 times 2 to the t over 3. And they are the same. E to the natural log, it all goes away. Cool. Now the part that's meant to review the calculus of it is to say, all right, if these two models are truly the same, they do the same thing, then their derivatives, so their rates of change should be the same. That's a basic truth, that if two functions are the same, the derivatives are the same. Okay? So, if the first one, if the first one, I'll call it A1 prime, is taken, that is the delightful derivative because it's E-based. Although it's got a little chain rule action in it. What's the derivative of that first one? 12 natural log of 2 over 3 for the chain rule part, and then still the natural log of 2 over 3 for the t for the derivative of the e staying the same, right? Okay. What about the second exponential growth model derivative? That's a review of back on Wednesday where we took derivatives of exponentials. Take the derivative of that, please. You remember the derivative? Say you don't remember the derivative. You could go off to the side and say, what the heck was that derivative of 2 to the x? What was the rule? How do we quickly do it? Yeah, we took the natural log, took the derivative. And so it is indeed 2 to the x natural log of 2, or in this case, 12 stays outside. Derivative then, 2 to the t over 3 times the natural log of 2, but we also do have that chain rule thing. What is the derivative of that t over 3? 1/3. Are they matching up? Although in a little different order, they're all same, yeah? All right, are we cool? Okay, I'll assume that's a yes. Let's go on to then a logical counter-argument, and that is, instead of derivatives of exponentials and logs, anti-derivatives of exponentials and logs. The first one is very intuitive. It's directly related to the derivative. The next one is not so directly related. Say you wanted to anti-differentiate 2 to the x. That's the derivative of something. What was the original? Now we just said, recall that we said when you took the derivative of 2 to the x, it was 2 to the x natural log of 2. Now, here's what the derivative should be like. We want this derivative. Unfortunately, we're lacking a little bit in that we have the 2 to the x, but we don't have that natural log of 2. What can I do to solve that problem? Can I just say, hey, I feel like bringing in a natural log of 2 here? Well, that's against the rules of math, unless you balance the expression with a divided by natural log of 2, which we're going to call that one up front, yeah? Well then, the 1 over natural log of 2 up front stays, but now the inside is a perfect derivative of 2 to the x, and so the antiderivative is just 2 to the x. The rule then is pretty straightforward. When you take the derivative of an exponential, it's 2 to the x times natural log of 2. When you take the antiderivative, it's 2 to the x, or a to the x, divided by the natural log of 2, or the base, whatever the case might be. Good luck. Very cool. It's a lot like the power rule, I suppose you could say. All right. This one, however, is not quite directly related to the derivative, because when I take the derivative of log base a, I don't get log base a. It's something totally different. So that's not the way to go. What's something I could do? If I don't like log base a, I could change it to log base e. Change of base. Do you remember the change of base formula? That's unfortunate. Would you write yourself a mini lesson? Change of base. Log base a of x equals question mark.
Just natural log, excellent. Yeah.
Yeah, natural log of x over natural log of a. That's the change of base formula. And it comes from saying, what is this? And taking a to the x and then taking the natural log and bringing exponents back down. You remember that process?
Yeah.
All right. That's getting me going. 1 over natural log of a is a constant I can bring out front, and now let's focus on that. How do we integrate natural log? Ultraviolet voodoo. It's integration by parts. It's not screaming integration by parts, but it's by integration by parts. What is the u? And the dv. And so du and v. So I get 1 over natural log of a times this big quantity. Ultraviolet is x natural log of x minus voodoo is 1 over x times x dx. So I get something like 1 over natural log of a, x natural log of x minus x plus a constant. Now you do not need to redo the ultraviolet voodoo every time. As long as you remember the natural log antiderivative comes from ultraviolet voodoo, that's good enough for me. And you can use the basic idea that if you integrate log base a, it's 1 over natural log of the base, whatever that might be. And the inside is the always same antiderivative of natural log. You follow? All right then. Well, that's a basic skill. Now let's employ it on a couple different levels, just like we do lots of things with integrations and come up then in lots of different types of problems. That first one, what kind of strategy are you thinking here? Okay, it's a product, so it's either U sub or ultraviolet voodoo. Which one? Ultraviolet voodoo. So what is U? X. dv then is the antiderivative of the exponential. What's the antiderivative of something to a power? Look at those notes up there. 1/2 to the x over
The natural log of
natural log of a half. Okay. Oops. Oh, sorry.
No,
I see what you're saying. I'm already at the antiderivative. Sorry. So v is 1/2 to the x. dv is 1/2 to the x. So v is 1/2 to the x over natural log of a half. Yeah? Sorry, I was getting ahead of myself. du straight up dx. So with ultraviolet voodoo, ultraviolet is x times 1/2 to the x all over natural log of a half minus, what's voodoo? Well, you have that 1/2 to the x over natural log of a half dx, yeah? So the first one's fine. I can leave it the way it is. That's cool. All right. And the second one, I can take the natural log of a half out, leaving me with 1/2 to the x again to integrate. So all I have to do then is integrate. What is the end result? When I integrate 1/2 to the x, now I'll have what in the top? 1/2 to the x, but in the denominator now I'll have squared. Yeah, I'll have to pick up another natural log of a half. See? See. All right. Try the next one on your own, or with a Mathamigo. Catch up to you, you're probably way ahead of me now. Are you going U sub on this?
Times 2.
So this is one of those cases where you fight the temptation to say, oh, zero, poo, I'm not going to even look at it, because with exponentials, when you put that zero in, you do get something, right? So at the end, I get something like 3 over natural log 7?
Yes.
All right. Any questions on that one? All right, dual purpose then. Getting your practice on volumes and this integration idea. Would you look at the next one here? You have this 2 to the x curve, which hopefully you know has a horizontal asymptote, and you know the x-intercept is at, or the y-intercept rather, is at 1. You know the basic shape of the curve, I assume. All those things are there. In this case, you're closing off with the curve on the upper, the x and y axis on the left and the lower, and x equals 3 on the right, and closing a region. It is crucial on these that you identify the region well. I can't tell you how many times I will see students get the wrong region and then do all this volumes work with the wrong region. So make sure you go about that part slowly. If you then revolve that around the x-axis, then you get a shape that looks something like a part of a horn or something like that, yeah? Or a speaker. Yeah. And the idea on volumes is sewing cylinders, right?
Yes.
So the big idea on volumes, I hope you learned this week, is that you're going to take the integral of pi r squared h in some kind of form, and then it goes to figuring out what's r, what's h. So what's r here? I heard somebody say 2 to the x, yeah. It is the curve, right? We're going, the radius is the distance from the axis, which is 0, up to the curve. So the radius would always be the function. Maybe that's squared, because the radius is squared. The height, what's the height of those cylinders? It's dx. It's really clean dx. The limits of integration, therefore, are 0 to 3. Here's where, again, it pays off to think a little bit groundwork-wise before you make your calculus bet. What's a good way to make our life easier here? Do the square first. So this is equivalent to 4 to the x. Yeah, 4 to the x is much nicer. Doesn't even look like it's squared anymore, but in our mind it really is. So what's the antiderivative of 4 to the x? 4 to the x over natural log 4 from 0 to 3. Pull that natural log of 4 out front and join it with the pi for a big old constant. And then I get 4 to the third minus 4 to the 0, which is 63. So I get 63 pi over the natural log. You see how that's going? Try the last one on your own on this side, and then we'll switch gears and go to a different idea on the back. We did.
That's what I just got. I don't know if that's like now. Now. So you such as X minus 2, right? Oh, I see. Square plus 2. What is that?
Yeah, thanks. So.
Wait, where are we supposed to multiply by 1/3?
So that it goes to 1.
Oh, but isn't it conditional? Like, okay.
Okay, so. All right, let's see how we did. So
Oh, I
leave a
see.
space, add a 7, add a 4 and subtract a 4, yeah? So 1 over x minus 2 squared plus 3, please. If you then make the 1, then that either means multiply by a third top and bottom or factor out of 3 in the denominator. Either however you look at it, you should be here afterwards, yes? All right, now we choose our u. What is this? Okay, now we choose our u. Let u equal, this needs to be u squared, so what is this the square of? X minus 2 over root 3. Therefore, du is
dx over root 3.
dx over root 3. And so dx is root 3 times du. So if I make my substitutions, this becomes 1/3, the top becomes root 3 du, which I suppose I can put out front, and I get my u squared plus 1. Right? Right? So when I put the constants out front and I integrate, I get arctangent of,
X minus 2 over root 3 plus c.
ahead of me, root 3 over 3, arctangent of x minus 2 over root 3 plus c. Yes?
How'd you get it where you pulled out the 1/3 and you divided by 1/3?
Here. So this is not how I think about it, but I don't want to put you guys say. To make this a 1, you need to factor out a 3, and if you factor out a 3, it needs to be divided out of both of these.
Yeah.
So when I divide a 3 out of this, it would be x minus 2 over 3.
Oh. Oh, okay.
And you can check that by saying, if I distributed, would it go back to where it was? Okay? All right, this last one, do you feel like you have it now and you don't need any more practice, or you want to try one more?
One more.
Okay, would you please change this? This is coming out arcsecant, which is not my intention. I would do that by a different method. So change this to 11 and try it. looking about what you have? All right. I suppose you could see this as just a 1 over root 2. I don't know. They'd probably leave it rational. If it's rational, so you might as well leave it. All right. Are we cool then?
Yes.
All right. There's another way of going about these we'll learn later called tricks. Some people prefer it. It's kind of a mixed bag. All right. I did not get through any. I got through part of 69, number 21 in the last class. So it looks like at the best we'll do that in this class. If nothing will be due today. So are you ready to at least maybe I can get you started on that once? All right.
You say 69?
69, 70, number 21, and it was y equals 6x squared, 6 over x, x-axis, and x equal k forms a region. And they meet at They meet at 1, if I'm not mistaken, and therefore x equal k being defined as greater than 1 is some kind of enclosing region, so you get this region here. Yes?
Oh, you actually, it's when you solve it.
So they wanted you in A to make a formula for the region's area as a function of whatever k is. I think you'll agree that if k changes, then the region area would be different. So it would depend on, so the first thing is there are two regions. There's one from 0 to 1 under the parabola, and then 1 to k of 6 over x. If I clean that up, then the antiderivative of that would be 2x cubed from 0 to 1 plus 6 natural log k from 1 to 6 natural log x. From 1 to k, I didn't bother using absolute value because that is a region that's positive anyway. So, at the best, 2 plus 6 natural log k is a formula for region R's area. Do you agree with part A?
Yep.
Okay. B is pretty easy with that. It says what it would take for k in order the area to be 20 units squared. So how would you figure out the k you would need for 20 square units of area? C equal to 20 and solve, and you get 18 divided by 6 is 3, and exponentiate it, so k is e to the third would yield an area of 20 square units. And then things start to get a little more funky. I don't think I'm going to get to part C, but it's a related rates problem at that time. It says if areas R is increasing by 8 square units per second, that implies that they're telling you dr dt is positive 8 square units per second. That means k must be growing to make that happen. So they want, what is dk dt when k is 27? With this equation here, the related rates problem will probably go fine if you just differentiate with respect to time. Remember, with respect to time. All right, nothing's due because we didn't get too much. So have a nice weekend. Set 7 days of gold sheet.
Wait, Mr.
Yellow. By virtue
Whenever you can see like.
Are you in Oh, no, you just for your, you would say, you would. That means D is root 3. So you need, you don't have them.
Yeah, this is what all of it.
She looks like she has red hair.
So in order, if you were to use the blueprint, just one minute, excuse me.